Okay, so the last section for this term, 1110. Taylor and Maclaurin series. So let's recall the notion of a power series. So power series is when we represent a function f as a bunch of powers of x minus a. So c n are coefficients. And that's an infinite number of terms. And we have a radius of convergence, which means that the series converges for values of x around the center A, which are separated which are no further than r, and r can be infinite or 0. Okay, so and we have seen a very limited number of examples of functions that can be represented as power series. Remember the first one that we kept coming back to? It was 1 over 1 minus x, and that had a nice power series representation. And the rest of the examples actually were some variations on the same thing. Either we replaced x with some other combination functions of x, or we differentiated, integrated it, and so on. A more general question is that which functions can be represented like this, and for what values of x, right? We want to see how general this representation is. Okay, so let's suppose that there is a function f that looks like this, and try to find out something about the function f from the numbers c0, c1, c2, and so on. What do these numbers tell us about the function f? So the first thing we're going to do, we're going to take this expression and evaluate it at a. So we say x equals a. So on the left we have f of a, right? Here we have c0. What about the rest of the terms? They're all 0. So this is a nice piece of information. Look, the first coefficient tells us the value of that function at a particular point, a. So this guy is responsible for the value of the function f at the center a. Okay. The next thing I'm going to do, I'm going to take this expression and differentiate it with respect to x. So f prime of x, when I differentiate it, c0 disappears, so this gives me 0. And I have c1. The next term gives me 2 c2 x minus a. The next term gives me 3 c3 x minus a squared. How many do I need? I don't know. Let's do one more. 4 c4 x minus a cubed plus dot dot dot. Okay, how can I use this expression? Again, let's set x equals a and evaluate this at a. So on the left I have f prime of a. On the right I have c1. How about the rest of the terms? 0. So the second coefficient, c1, tells me the value of the derivative of f at a. Okay. Next, I'm going to take this expression and differentiate it once more with respect to x. So I get f prime prime on the left. And on the right, this gives me 0. This is 2 c2 plus 3 times 2 c3, 4 times 3 x minus a squared, and so on. Okay. Using the same procedure, take x equals a. What do I get? F prime prime of a is equal to 2 c2. Oh, something is wrong.
There should be an x minus a term after 2 times 3 c3. Yeah.
C3, yes, x minus a. Thank you. Okay. 2, C2, and the rest of the terms is 0. So we thought we guessed the pattern, right? We thought that each coefficient tells me the first, the second, and so on derivative of the function f with respect to x at point A. Not quite. Here I have a factor of 2, so I have to do a little bit more work, okay? Because I don't know what happens. So let's do the third derivative. So I have to take this expression, differentiated. Okay, and evaluate it at A. So the third derivative at A is given by 3 times 2 times C3, and the rest of the terms do contain a power of x minus a. Let's do one more. F4. So I have to take this expression and differentiate it. I only have one term. Okay, I have 4 times. Oh, and I forgot the coefficient C4 here. Sorry. This is terrible. 3 C4 like this. Sorry. So I have 4 times 3 times 2 C4 plus something else. So evaluating at A, I get the fourth derivative. That is equal to 4 times 3 times 2 C4. Okay, let me summarize. So C naught is equal to f of a. That's from the first experiment. C1 is f prime of a. Okay. C2 is f prime prime of a divided by 2 from this expression. Remember that number 2 that popped up? C3 is f, the third derivative, at a divided by 2 times 3. C4 is the fourth derivative. That's from here, divided by 2 times 3 times 4. I now ask you, what is Cn? Guess the pattern.
F to the n of a.
F, nth derivative, evaluated at a.
Over
N factorial, yes. Okay. So one question. So I can see 2 factorial here, right? How about this one? This is 1 factorial. That's okay. This one, so we have to make some notation. So what is 0 factorial? Is 1. And what is f? The zeroth derivative. That's when you take a derivative 0 times. So that's just f. Okay. So everything is great. We have a whole pattern that works for any index. Okay. So this is a very nice discovery, which we can formulate in the following theorem. If f has a power series representation, at A, then f of x is given by this formula, where Cn is f, nth derivative of f at A divided by n factorial, which allows me actually to write this formula in a more explicit fashion. I have f, nth derivative of A over n factorial, x minus n factorial. Okay, this is called the Taylor series of function f at point A. point A. And there is a special name for this series when we expand at A equals 0. So we can write down f of x set A equals 0. Okay. This works for any A, so let me write the special form at 0 is called the Maclaurin series of function f. So when you write down the Taylor series at 0, this is called the Maclaurin series. But nobody uses that. At least, well, not in my area of math. Okay, so there are a lot of if statements here. This expression, or this, only makes sense if it converges, right? And we said that if f of x has a representation as a power series, then this is true. So we don't actually know whether this converges, and we don't know if it converges, whether it converges to the function f. These are still things that we have to address. Okay, so but we'll work with some examples. Find the Maclaurin series of function f of x. Oh, f of x equals e to the x. This is the easiest series expansion. And its radius of convergence. So if f of x, in order to write down the Maclaurin series, I have to evaluate the derivatives of f at 0, the infinite number of them, right? The first derivative, the second derivative, and so on. Let's do it for the exponent. So if f of x is equal to e to the x, then what's f prime of x? How about f prime prime?
E to the x.
Yeah, and so on, right? So we can say that f n of x is e to the x. What we really need is fn of 0. Fn of 0 is e to the 0, which is 1. So all of these are 1. Okay? That's why it's the easiest. So we can say that we have the sum from 0 to infinity, x to the n factorial. And I'll write it down, skipping the sigma notation, just to show you what it looks like. So when n equals 0, we just have 1. And then we have x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 to the 4 factorial, and so on. Okay. Fine. Find the radius of convergence. We always use the same method to find the radius of convergence. We look at the ratio test. Okay. So what is an? Use ratio test with an. What's my general term? An is equal to x to the n over n factorial. So we have an plus 1 over an is x to the n plus 1 factorial divided by x to the n factorial, like this. So x to the n cancels. I have 1x here, and I have n plus 1. what happens to this when n goes to infinity for any fixed x? Goes to 0 as n goes to infinity. Therefore, the series converges for any x, right? The radius of convergence is infinity. The exponent is very nice this way. It's Maclaurin series converges for any x. Question?
How did you get x to the n over n factorial from e to the x?
This one?
Yeah, how'd you get that from e to
So this is the general formula. Okay? So x to the n is there, n factorial is there. The missing component is the derivatives of my function evaluated at 0. My function is the exponent. All the derivatives are exponents. Evaluated at 0, they all become 1s. Okay? More questions? Okay. So how do we know whether a power series converges to whether the Taylor series converges to the target function f, right? We can take a given function f, write down this representation, and even evaluate its convergence. We'll say, okay, it converges. But where does it converge to? We should still evaluate the limit, okay? And most importantly, we should figure out whether it indeed converges to the function f, right? So the general method of doing it is to compare the series with the target function f. So does this converge to f of x? Right. So we have to evaluate the difference as n goes to infinity. Right? We want to look at partial sums. Partial sums. And we want to figure out what, how close they get to the target function f as n goes to infinity. As n is where I cut my infinite summation. So I'm going to sum from from 0 to capital N, and take the difference between the partial sum and the target function. And I want to make sure that as n goes to infinity, this goes to 0. Okay? This is called the remainder. Okay. Rn of x is defined as n these are all the terms that remain in the infinite sum starting from number n plus 1, sorry. So starting from n, okay. We want to show that Rn of x goes to 0 I'm sorry, this I confused. The notation. this is the definition. Okay. So it's the difference between the target function and the first n terms in my summation. I want to show that this goes to 0 as n goes to infinity. And there is a theorem that appears without proof, right, that allows us to calculate, reason about this quantity. So if f of x is given by Tn of x plus R n of x, where Tn is all the terms from 0 to n and I just defined Rn, and the limit as n goes to infinity of Rn of x is 0 for x minus a inside the radius of convergence, then we can say that f is equal to its Taylor series. For x inside the radius of convergence. So basically, if we can show that the remainder goes to 0, then f is equal to its power series representation. So what we have to somehow get a handle on this remainder. So here's a theorem that helps us do this. It's called Taylor's inequality. If we can show that the derivative of order n plus 1 of x is bounded inside the radius of convergence, then Rn of x satisfies the following inequality. Okay. So I will show you, just write it down now, and I'll show you what it means. So we will use an example, this example, the example of the exponent. Okay. So what have we done so far with the exponent? What were the logical steps? We've done 2 things out of 3. We have evaluated the terms in the Maclaurin expansion, okay, by calculating all the derivatives, which are all equal to 1. So we wrote down the Taylor series. Okay, that was one step. The second step, we calculated the radius of convergence. That was infinity. The third and final step is to show that this series, when it converges, and it always converges, that it indeed converges to this function. Okay, and to do that, we have to show that the remainder goes to 0. This is what we'll do now. Okay, prove that e to the x is equal to its Maclaurin series. So we need to show that Rn of x goes to 0 as n goes to infinity. So suppose that x belongs to some interval from minus d to d. Okay, we are going to put a limit to the values of x. So let's suppose that x belongs to this interval. What can we say about the n plus first derivative, f n plus 1 of x inside this interval? So the derivative of the order n plus 1 of the exponent is actually equals to the exponent, okay? So what does the exponent do? It's some function that looks like this. This is e to the x. So on an interval between minus d and d, it's a growing function of x. And the biggest value that it achieves is given by e to the d, right? So we can say that f n plus 1 of x, the absolute value, is less or equal than e to the d. Just because this function is simply an exponent, in this case, the exponent does this. It never grows larger than e to the d. Okay? It's a finite quantity that bounds this derivative. And now we go to this theorem, to Taylor's inequality. From Taylor's inequality, we know that the remainder on D is less or equal to m, the bound for the derivative, divided by this times this. So we have e to the d, okay, n plus 1 factorial x n plus 1. Okay. So for x in the interval bounded by d. Okay. So this is the value of m. Now we take the limit. The limit as n goes to infinity of this quantity e to the d n plus 1 x n plus 1 is the same as e to the d, because that's a constant, x n plus 1 factorial. Okay. What's the limit of this quantity? We've had this example before, and it's equal to 0. Okay. So therefore, because the remainder, the absolute value of the remainder is smaller than this quantity, and this quantity tends to 0, by the squeeze theorem, we can say that the remainder itself goes to 0. Therefore, Rn of x goes to 0 as n goes to infinity. So this proves that e to the x is equal to its Maclaurin expansion. Okay. So this is a famous formula, and it allows many calculations that otherwise would be impossible. If we don't run, I'll show you today what we can do with this, just for this particular function, the exponent. Okay. So I want to show you some other Taylor series of different functions. You will see that it's sometimes quite easy to calculate them. So as the next example, we'll find the Maclaurin series for function f of x given by sine x. Okay. So go back to the general formula. We need to populate the series with the nth derivatives of sine at 0. So the zeroth derivative is the same as f of x, is sine x. The first derivative is cosine x, right? The second derivative is minus sine x. The third derivative is minus cosine x. The fourth, what is the derivative of minus cosine x? Sine x. And you can see that this closes in circle. So we go from sine to cosine to minus cosine, and then back to sine, and it repeats. So as we do it for an infinite number of derivatives, we're going to have this repeating cycle. So there are going to be no other functions, just these. Okay? Here, I don't need these for any x. I need to evaluate them at x equals 0. So to set x equals 0, we have f of 0 is 0. The first derivative is 1. The second derivative is 0. The third derivative is minus 1. And the fourth derivative is 0 again. And it's going to repeat. So what is the sequence? 0, 1, 0, minus 1, 0, 1, 0, minus 1, 0, 1, and so on. Right? These are all the derivatives of sine evaluated at 0. Okay? So let us use this information to write down the Taylor series for this function. So sine x is given by f of naught, f of 0, 1 of 0, x, this is the general expansion. Here I haven't put any information about the derivatives yet. I'm going to do it in a second. Let me just go to the fifth term. Fifth, 5 factorial, right? And so on. Now we are going to populate it. The first one is 0, 1, 0, minus 1. So I have nothing. I have 1. Nothing. Minus 1. Nothing. 1. What's the next term? What's the next term? The next. What's the next non-zero term? Yes. Absolutely. 7 factorial plus x to the 9 factorial minus x to 11 factorial. And so on, right? You can see a beautiful pattern here too. How do we write it? As a sigma notation. So you can see that we only have odd terms. Okay. So if n goes from 0 to infinity, it goes 0, 1, 2, 3, 4, 5. I want to look at the combination 2n minus 1 plus 1. What does this do? Okay. When n is 0, this is 1. When n is 1, this is 3. When n is 2, this is 5. So as n goes 0, 1, 2, 3, 4, 5, this goes 1, 3, 5, 7, 9, 11. Right? So this is a machine that only creates odd numbers. Okay. So I'm going to use that. I'm going to have the alternating sign incorporated like this. X comes in the power 2n plus 1. These are all the odd powers of x. And in the denominator, I have the matching factorial. Okay. So this is the Maclaurin series of the function sine x, written in terms of sigma notation. Questions? Okay. Now, how about cosine? So in principle, every time you do this, this is a nice way of doing it systematically. On the left, you write the function, its derivative, second derivative, third derivative in general. So the next line is a differentiation of the previous line. On the right, you take all these things and evaluate them at A, whatever your center of your series is. Okay? So when we do it for cosine, we could do the same, but we don't do it. We do something that is easier. So the example, find the Maclaurin series for f of x equals cos x. So what I'm going to do, I'm going to take this representation of sine, and as you remember, we can actually differentiate power series. So by differentiating the left-hand side, I get cosine, and these are power series, right? They're very easy to differentiate. So differentiate the series for sine x. So on the left, I get cosine x. On the right, I have 1, okay, minus 3x squared, 3 factorial, plus 5x fourth over 5 factorial. I'm differentiating these terms, okay, explicitly without the sigma thing. Minus 7x to the 6, 7 factorial, plus 9x to the 8, 9 factorial. That's enough, okay? So, and you can see that we have a nice cancellation. You have 3 factorial divided by 3, 5 factorial divided by 5. So what can I replace it with? This is just what? 4 factorial, right? So I have 1 minus x squared over 2 factorial plus x to the 4th, 4 factorial, minus x to the 6th, 6 factorial, and so on. Okay, so now we only have even powers. So I'm going to write it down as the sigma notation. I have the alternating sign, but I don't want all the n's. I only want even n's. So as n goes 0, 1, 2, 3, 4, 5, 2n goes 0, 2, 4, 6, 8, 10, right? So this is what I want. So I have x to the power of 2n divided by 2n factorial. That only picks out the even terms. Questions? Very good. Fine. Another important series, which will do the usual method. By usual, I mean that we're going to write down all the derivatives and evaluate them at the center. So find the Maclaurin series of the function f of x given by 1 plus x to the k, some power of k. Okay. So I'm going to need f of x, all of these. So 1 plus x to the k. This is my given function. The first derivative is k, 1 plus x, k minus 1. The next one is k, k minus 1, 1 plus k, k minus 2, k, k minus 1, k minus 2, 1 plus x, k minus 3. So I think we can see the pattern here, right? And it's especially transparent when we evaluate everything at x equals 0. So what is f of 0? You can see that this is 1, right? When x is 0, this is 1 to the k is 1. F prime of 0 is given by k. The second derivative is k, k minus 1. The third derivative is k, k minus 1, k minus 2, and so on, right? What's the nth derivative? What's the nth derivative? We're going to have k, k minus 1, and so on, all the terms. What's the last term? Are you sure? This is F3. The last term is k minus 2. K minus plus 1, yes. OK, like this. So, because subtracting n would subtract too much. So I need to put one back. Fine. So we can write down the series starting from 0. The general term is k, k minus 1, k minus n plus 1, dividing by n factorial, x to the n. This is a general expansion, the Maclaurin expansion of this function. So I want to give you a better way to write this. Okay, you can see that what you do here is you multiply all the numbers starting from k and going down. So for instance, if k was equal to 10, you'd have 10, 9, 8, and you stop at some point, right? So there's a much better way of writing this. So if I went all the way down to 1, this would be equal to k factorial, right? If I went all the way down to 1. However, I stop. And starting from k minus n, I don't have these terms here. So if I put in the denominator k minus n factorial, that's what this is, right? So I have all the biggest multipliers, and I multiply them together, 10, 9, 8, and then I have to stop. Where do I stop? The last term I include this k minus n plus 1. The first term that I exclude is k minus n, and everything down below from that. So this gives me the equivalent representation in terms of factorials. Okay, so this allows for a nicer representation here. So I have k factorial, k minus n factorial, n factorial, x to the n. And these things are called binomial coefficients. And there is a notation for them. It's called k choose n. Okay, so this is a notation that means exactly this. What's music? Okay. If you're familiar a little bit with combinatorics, that tells you how many ways you can pick. If we have k students in the class, and I want to pick a group of n. This is how many different ways I can pick n students out of k. Question?
Like, can you tell them to be quiet or I'll cut them?
It almost doesn't make sense because we have 2 minutes left.
Okay.
Yeah. The last, let's talk about the radius of convergence really quickly. Question to you: how do I evaluate the radius of convergence of any power series, including Maclaurin series? What do I do? What is the method? Ratio test. Okay, so an plus 1 over an. I take, so what is an? An is k factorial over k minus n factorial x to the n. K factorial k minus n minus 1 factorial n plus 1. Is it getting louder? Divided by k factorial k minus n factorial x to the n. So look, we have lots of cancellations. X remains only here. K minus n factorial, k minus n minus 1. So I have k minus n, and I have n plus 1. Okay, so I can write it once more like this: 1 minus k over n divided by 1 plus 1 over n. Okay, so what is the limit of this as n goes to infinity? So before, when we did it for the exponents, we had x divided by n factorial, and that always went to 0. This one, as you can see, doesn't go to 0, but it goes to x factorial. So the ratio test tells us that the series converge only when this guy is less than 1. So the radius of convergence for Maclaurin series is 1. So we have this nice representation of this function for the values of x between minus 1 and 1 only. Questions?
So that's the 1 minus k over n. That you have to find the limit of that, right?
So yes, n goes to infinity. So this guy goes to 0. So I have 1. This goes to 0. So I have 1, and x remains. Thank you.